Okay.
Where's John?
I don't know. We've already established, when I planned this thing out, I didn't expect we would get so far so easily. And so I thought it would take us almost a week to get to where we are. And therefore, I feel very happy that I can use the remaining days to do this. First, we've noticed and demonstrated by telling you what happens in an experiment without actually doing it, that ordinary ideas will not work. You've got to be very careful with the logic and so forth to handle what happens in real nature, in quantum, what we call, now we've developed a theory called quantum mechanics, which
What's unreal?
Nothing, it's just a mistaken phrase, okay?
It's a little early to start on that.
And, but we can't just be satisfied with saying that some particular set of ideas will not be satisfactory to describe the situation. The problem was to find out what set of ideas would be satisfactory to describe the situation. As a matter of fact, those ideas were discovered before the difficulties were discovered. And it's the ideas of quantum mechanics is that I want to describe now is a positive thing. It's a way that we actually use to make calculations and understand nature. Excuse me, to make calculations. We really don't understand it very well in the way that I've explained very carefully before, and I won't go over that all the time. I might say, make mistakes like that, talk about real nature, understanding real nature we are unable to do. At any rate, what I would like now to use in the remaining time is to, if I might try, to tell you actually what physicists do when they make calculations, so they can predict probabilities for events, right? And they predict correctly the probabilities of events for all the experiments, at least in a certain range where they know some things about electrons and photons and so forth, light and matter and chemistry and ordinary phenomena, not involving gravitation in detail or nuclear phenomena in, well, actually today I used to say those as excuses, but the nuclear phenomena are now probably under control too. But at any rate, for a vast array of phenomena, ordinary phenomena, we have this quantum theory. And as you might well expect, the quantum theory, I mean, as a result of our previous lectures, the quantum theory is just crazy. It doesn't explain anything. It just gives you numbers. It gives you the right probabilities. And I'm making no excuse for that now because I've told you how funny real nature is. So I'd like now to describe what these funny guys, the physicists, actually have to do to make the calculations, and so that you would see what it looks like. In other words, what their view of the world really is. It's even more correct, a description of what the physicist does or how he looks at the world when he's making predictions. And so I start with the simplest phenomena that we can discuss. And the first one I want to start with is the phenomena of light. Early on, when light was being investigated by Newton, he thought that the light that came into the eye was like a rain of particles, like raindrops coming in. That more light meant more particles coming in. That light, he discovered, could be separated, white light, into different colors, light in the spectral arrangement. And one kind of color light would be one kind of raindrop, and another kind of color would be a different kind of raindrop, and so forth over the whole spectrum. And they would be running into the eye, and that if we would someday ever have sufficiently delicate instruments, we would presumably discover that it was like a pattering rather than a smooth current coming in. That if you tried to measure very weakly intense light, you would go click, 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 as the particles came raining down. It's as though we have a lot of rain on a big area, because we, at the beginning, have crude scales and crude experiments, and we're trying to measure rain, and all we have is a pan 50 feet across. All we can measure is the weight of the water that comes down. We can't feel the individual drops. It's too subtle. But if we would take very fine 1 square centimeter tin and measure the force, we'd suddenly discover that it's irregular, that the rain is a bumpy business. That's what Newton expected, and he had this theory of particles. He also discovered a very interesting thing, which we've talked about, the light from the soap bubbles, or light from thin films. The brightness of reflection from a thin film depends upon how thick the film is. As the film gets thicker and thinner, it gets brighter and darker. That was hard for him to understand from the point of view of particles. Finally, a theory of waves was invented, which explained that very easily, and we talked about that, how with the waves fitting into the space, or not fitting in, we got strong or weak reflections from the surface. And so everything looked all right. It would be waves and not particles. And then the instruments got better and better until we measured light very precisely, like instead of the 50-yard thing to measure rain, it was 1 centimeter. And lo and behold, to our horror, it behaved like particles. The most sensitive instruments we have to measure light, for example, photomultipliers, discover when the light is weak that it's nothing but the multiplier goes off, bing, 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 as the particles seem to be coming in, okay? All the experiments, when you're measuring light carefully and when it's strong, there are so many particles coming in that the instrument sort of gets swamped and you can't be sure that they're individuals, but that's just technical, because if you put some kind of screens in or put more better instrument or whatever, then you discover again that they were individual particles. If you have a situation where the light is to go to one, if you have a situation where you have a source of light that's very weak and you put a photomultiplier, you get this individual clicks. If you had a room like, or an area with a very weak light and had photomultipliers all around, then at any moment one will go off but not the others, or another will go off, a small number of bullets being shot out from a center. Then it would hit in one place or another place. So if you put photomultipliers all around, it checks. They don't both go off at the same time. They do that rarely, because if you're spitting bullets at random, maybe by accident 2 come out. But if you decrease the light intensity, that means make fewer photons, we call these bullets, per second, then the number of coincidences goes down as expected. And so we see that the light behaves exactly like particles. The different colored light, light red or blue or green and so forth, spectral light, correspond to particles of different energy. That is, the energy comes in lumps, and these lumps have different sizes for the different colored light. Now, what I want to describe, that caused, by the way, that caused a certain amount of trouble, because it was hard to understand. In fact, virtually impossible to understand this effect that the reflection of light at from layers of different thicknesses varies by using particles. And yet, when you measured it, it was particles. And that makes a problem, which I want to describe now. Yes?
For Deguan, would it be possible to describe a photon, in physical space, what it would like, a specific photon, let's say, sodium?
No. All we know is we get a click and a counter. Where it is or what it looks like, we have to decide on by the properties, okay? As you've already learned from the previous discussion, we're going to have a lot of trouble in picturing anything that we haven't directly measured. If we try to say how big a photon is, or how it's spread out, or what it looks like, we're going to get in some difficulty with some experiment. It isn't going to behave that way you'd expect. So you're going to be very disappointed, because it's going to be impossible for me to tell you how big a photon is, where it is, and so forth. Nevertheless, depending on your point of view, I'll tell you a series of crazy rules by which you can tell exactly what will happen in any experiment with photons. What's the chance that the multiplier will go off in this situation, that situation, without ever having been able to say what the photon looks like in a certain sense, okay? In the sense of some sort of model of waves in space. That's just a reflection in another level of the same difficulty that we had with the boxes that we were talking about last 3 days, that there just isn't any way to say, well, what is behind those buttons? What is it that makes the buttons make red and green? If we start to say that, we're going to get into difficulty. And it's exactly the same way. For this purpose or for that purpose, you can say what a photon looks like. And in that experiment, it'll work okay. But you can design another experiment, measure something different in the same circumstance, in which you won't be able to use your model to get it. It's much like this. If I always was pushing button number 1, never the 2 and 3, always measuring the same thing, that would make an easy problem. There would be not any complication in explaining what kinds of results we got. But if you allow that you might have measured something else, you'll see you're beginning to get into these puzzling difficulties. And so to make a complete theory, we cannot do it with a model. We can only make an incomplete theory. And what my purpose is today is to tell you the complete theory, not the incomplete approximations, okay? Because those are all in all the books and easy, and there's nothing, but they may not be easy, it depends on your mood, but they're there. And this fun of this is to talk about the way it really looks. Or we don't know what it looks like, what we really do. Okay? Okay? Now, what?
Somebody watched inappropriate outside conversation.
Oh, yeah, right, okay. So we have to get the idea then that light, when we measure, we're going to measure all the time with these wonderful devices, which are photomultipliers. You might want to know how they work, actually. It's just technically a small thing. It's a light photon, when it hits certain materials like sodium surface or cesium, which is actually what's used, when the photon hits it, it knocks an electron out, an electrified particle. And then we could put another plate here. Let's say this is minus and make this electrically plus. So the electron is accelerated and comes to this plate. One electron is rather difficult to measure. It's such a tiny amount that it's very, very difficult. So we need an amplifier. But the amplifier can be done automatically, because if you have this voltage, about 200 volts, when the electron plows into this piece of metal, it like makes a splash. There are electrons in the metal. And knocks a few of them out, let's say on the average 5. It varies. Then we have another plate here that attracts those. And when those have got enough energy and bounce, each of these 5 hit this, then on the average they make 5. That makes 25. And then another plate and another plate, maybe 7, 8 plates. Each time multiplying by 3 or 4 or 5. And by the time you get up here, you got a tremendous host of electrons by this amplification process inside a vacuum. So one photon starts this whole thing going, and there's a like big avalanche, so to speak. And by the time you get to the last plate, there's so many electrons that it represents an almost macroscopic charge or current, and then we can go through normal amplifiers and electric circuits to light lights and tell us we've got a count.
Red or green.
Yeah, or whatever, to decide whether we have a count or not, okay? It goes off, click. Click is a loud noise. It requires a relay to kick something to make a noise. That relay takes a lot of current. That's amplified from here. And that was already the result of amplifying the result of one electron multiplying up. So all of the devices that we have, you must appreciate, are enormous amplifiers, because we're so big and the atoms and photons are so weak and small that to see any of these effects have to be very delicately, we have to amplify it a great deal. It's possible that this amplification, this perpetual amplification that's necessary, has a lot to do with our difficulty of understanding things on a small scale, because we only can see things on a small scale after they've been amplified in one way or another. But aside from that philosophical hokey poke, I now suppose that we have these photomultipliers. What does it mean when light is more or less intense? First, I told you what it meant, color. The amount of energy that this first electron is kicked out with depends upon the color of the light. I should have explained that. That was an interesting thing. If you, with light, it's a little hard to arrange, but you could do it with single atoms instead of a metal. But never mind. With a photon, you'll knock out an electron which originally had a certain energy. If you have, that was red light. If you have blue light, the electron that comes out has a higher energy. Each color light corresponds, therefore, to a photon of a certain energy, we say. The brighter light just means more photons. So when the light is weaker, it just means that there'll be less counts per second on the average, and brighter light is more counts per second. Of course, the counts don't come steady, pick, 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 but irregularly, accidentally, bonk, 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 and so forth. And we talk about the average number per second. Yeah?
When the different colored light comes, it would bump off an electron of a different energy level, so to speak.
A different energy.
So a red one would bump off
A faster, not as fast an electron as a blue one would. However, these devices, the photomultipliers, are not particularly, they don't care, because they accelerate the electron anyway, and they work with all the colors. They're built to do that. If you want to build one which is more sensitive to one or another color, you can, using either the energy or put something in the way so that only certain kind of photons can come out or something. What we're going to do now is to talk about to make it easy for ourselves, we don't want to talk about too much at once. And so we'll suppose that all the light we're talking about is exactly one color. By the way, we tried to do something with the soap bubbles out there with looking at them in one color by putting them in a spectrum that was shining through one of those prisms outside. But it really was, from an experimental point of view, you liked it, but it was almost a failure because there was so much light coming from everywhere else. That is, light was coming through the windows other than the prism. And that light, you were also seeing reflected in the thing. Just like I can see in your eyeglasses now, reflections of lights all around, even though the most important light is that light. That's not the one that's lighting up, making the reflection for me in the eyeglasses. In the same way in those bubbles, although the most important light might have been, the brightest part might have been from the prism, we were seeing reflections from windows and other things, and it was all very complicated, and that's no way to do an experiment out of control like that. Much more satisfactory would be to have all the light of one color that's in the room so that you're studying it. And it's easy to arrange that. At night, they have in various places in the countryside and stuff, they have these yellow street lights. If you live where there's a yellow street light, that's a sodium light, and that emits light all of one color. Then take the soap bubble and blow it at night in front of that, and then you'll see the bands I'm talking, very fine. In fact, it's so good, the light, that you can take any kind of thin layered stuff, even very thin glass or something like that, and if you're careful and hold it just right, you can see very fine bands, even in a reasonable size thickness, because it's so accurate. But let me suppose then that we do have light, like from sodium vapor, so that all the light I'm always going to talk about is always photons of exactly the same energy. We call it monochromatic, one-color light. Good? Now we start out with the properties that have to do with intensity. The first thing we've been talking about is reflection from a surface. So suppose that we had a surface, say, of water or of glass, a single surface. Here's glass, and here's air, or vacuum, practically, let's say. Now suppose that we have a source of light, and then we shine it this way, straight up and down. I'm making everything easy the first time. You know, the world is more complicated. We'll make a simple situation. Then, as everybody knows, the light goes down into the glass. And as everybody knows, you see a reflection also. That means that some light is reflected. It's partly reflected. If you'd measure so much energy per second coming down, that's the intensity of the light, you'll find that something like 4% is reflected by the glass and 96% goes through. Right? That's called partial reflection. And all of a sudden we have already our great difficulty. Because this is photons. If this weak is made very weak, and we put a photomultiplier here to look for the reflection, and we put a photomultiplier to look here whether it's there are photons coming this way. As a matter of fact, we can even measure when a photon leaves here, so we can even, but let's suppose that we forget that. We get number of photons counted in here. Pip, 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 pip is much higher than in here. And this counts only 1/25 or 4% of all the photons that are coming out of here. 96% are counted here, okay? When the intensity is low enough, both of them never go off. If they do, it's a coincidence. You lower the intensity, it happens less often. So we say they don't ordinarily go. One photon either arrives here or here. I could make this source so weak that one photon comes every few minutes. And we know at the speed of light that whatever it did, it finished before the next photon. So one photon at a time either lands here or lands here. You don't have 1/25 of a photon landing here. That's important. Just one photon either lands here or lands there. What then is partial reflection? It can only mean that the next time you try it, let's say the first one landed here, the second one landed here, but every once in a while, 1 out of 25, it comes here. It must be probabilistic. It comes, that's what happens. We discover that it's statistical and accidental, that the photon figures out whether to go here or here. If I could use that horrifying language, I don't really mean that. But it lands here or here, 1 out of 25. Okay, it's not so bad. But you say, how does the photon make up its mind whether to go here or here? In other words, what kind of a picture of a photon can I make so that I understand that a 25th of them go, 4% of them go up there? One possible theory. There are little spots here. They're so small we can't see them, little dots on the surface. They only cover 4% of the surface. If a photon happens to, usually, as it doesn't hit one of those dots and goes right through. But once in a while, it hits one of those dots and bounces back. That's my theory. It's all kind of deterministic. It depends on where these dots are. There were various arguments that Newton made to show that there were no dots. Yes?
Could that experiment be so, if that were, could that experiment be so carefully controlled that the photon would pass through virtually the same point in the
No.
glass each time?
No, you can't do that.
Because of the,
When you make monochromatic light, you can't focus it any more sharply than about what's called the wavelength. No matter how you do it, you can't determine where it is better than a certain width if it's monochromatic. And so therefore you can't quite do what you want to do. Yeah. But Newton gave arguments which were great and very ingenious for his day about why there aren't any spots. I won't review them. They're historically interesting, though, to see how he could have deduced that at that time. However, I'll continue to describe the properties of reflection to a point where you'll see that the dot theory must be wrong anyhow. So I won't use Newton's argument. I'll use a different one. All right? Now, the fun of it is, so far, let me just tell you, it ain't going to be dots, and you'll see why it ain't going to be dots later on. No mechanism has ever been invented to explain what makes each one go up or go down. This is the kind of world we're in. We learned that we're going to be in that kind of a world. It's going to be probabilistic. All we're going to have is a theory that calculates the chances, and it doesn't determine for each photon which way it's going to go. It can't be done, all right? So, next experiment is but I wanted to explain what intensity was. It was the number of photons, and that therefore partial reflection is already a semi-mysterious process. Already we have trouble, even with partial reflection. But it gets more interesting when we realize, when we study what happens if we have thin layers. If we have a layer of glass that's only so thick, and we ask what the reflection is and how much is transmitted. Well, offhand you'd say 4% comes from the first surface, but when it gets to the second surface, it's possibly reflected again. As a matter of fact, it'll come out again another 4%. And so you'd say that the number that would come here would be 8%, or yeah, that's the best way, 8 out of 100 instead of 4 out of 100. And that 92% would come through. That's what you'd guess. And that seems to be right if you do the experiment carelessly and have the glass fairly thick and the edge is not perfect and slightly irregular. You don't measure everything very accurately. It'll look like that. But if you're very careful to make all the things very plain and flat and make it, especially if this is thin, you'll discover this is not what happened. What does happen? All right? See, there wouldn't be any problem with this. We could have the spots here and then the spots on the back of this surface. And if it missed the first spot, it has a chance to hit the second spot. That's why we'd think 8%, because it's 4% chance of hitting the first spot and almost 8. Of course, there's a slight correction. The first one would remove some, and so there'd be 96% to hit here, but that's almost 100%, so I just added. It's 4% of 96 plus 4. It's too complicated. It was just, roughly speaking, 8, okay? It mostly goes through. So, but what actually happens when we look at it is that we see that the amount of reflection of the light depends on the thickness. It gets bright and dark depending on the thickness. Just like we talked about oil colors. When we have a thin film of oil, we see colors. If we would do it with monochromatic light of one color, instead of seeing colors, we'd see bands of bright and dark, bright and dark. If we had two colors, the bright and dark bands would appear in different places on top of each other. And that superposition would make it a mixture of colors. And so we see a large number of different colors when we use white light on a film. But if we used, as Newton demonstrated, monochromatic light, any one color simply produces bands of light and dark. And these bands, as Newton found, depended simply on the thickness of the layer. And so we could measure how much is reflected depending on the thickness of the layer. And it comes out as follows. Now, these numbers are approximate. I'm doing things like taking 96% to 4% and calling it 4%, because it's nearly right, okay? So in that approximation, these numbers are. So this is the percentage of reflection, and this is the thickness. right? Turns out if the thickness is 0, there's no reflection. Nice. No, there's nothing there, so there's no reflection. Then it builds up. As you thicken it, the amount of reflection goes up. You know how to read such a graph. That means at this thickness, there's this much reflection. And it goes up and climbs up to a height, which is in fact 16%. Unusual, it's not 8%. But then if you make it still thicker, it comes down again, and there's a thickness at which is 0 again. Then if you make it thicker, it goes up again to 16%, and then comes down again with a thickness that is 0 again. And this keeps on going. If I were to draw this on and on, it has been done experimentally for millions or hundreds of millions of these things, and it keeps right on going up and down, up and down, up and down as you keep this thickness increasing and increasing and increasing. If everything is done very carefully, then you can follow these ups and downs all the time. We talked about this. Different thicknesses reflect well, or another thickness doesn't reflect at all. Yes?
When the thickness is 0, the reflection is what was it?
No, it's 0.
It's not there.
It's not there.
Oh, you're not looking at film on the substrate, okay.
No, it's just a thin layer of glass. There's nothing underneath the glass. I should have explained that. This is also air. If there was water or something down here, it would be more complicated. I'm trying to make it easy. If there's no glass, there's no reflection. Nice. But actually, although it's nice, it would have been quite a mystery, because a very thin layer of glass, if there were spots on it, would make spots, and you'd have the 4%. And the fact that the bottom layer was very close to it wouldn't make any difference. Already we know it can't be spots. So, but the thing that's very exciting is that there's a certain thickness at which it's 0, and that repeats and repeats and repeats and repeats and repeats. Now, according to the wave theory, that turned out to be fairly beautiful but easy to explain, as that we talked about it, the waves bouncing from here and the waves bouncing from here would both come together with their crests opposite, crests and troughs, and cancel out. Whereas if the thickness was something else, then the timing being different, the crests would superpose, that is, they would add to each other and make more strength, and that corresponds to this case. You'll notice, by the way, that the average for great thicknesses over here, if the thickness is not exactly even and things are done sloppily, you get the average effect, which is the 8% that you expected. That's why large things, gross things, where you're not careful, produces the normal probabilities and everything that you would expect, let's call classical logic. But these funny ups and downs, these are called interference effects, which you need to be a little bit delicate to measure, but we got delicate when we started to measure atoms, and this isn't even in atoms. This is easy to find experimentally, even in soap bubbles, so, and on the street in oil films. So it's relatively easy to discover this phenomenon. This phenomenon is really not puzzling if the light were waves, but you remember that we discovered that it behaves like particles. So what this is, I say 16%. What is it 16? What is the 16%? It's the probability. What we're plotting here is the chance or probability of reflection. Now let's see how frighteningly confusing that is. Because let's say, suppose that I took a thickness, a very thick, I got the 4% corresponds to the front surface. Suppose I bent the back surface, or I didn't have it, and I got 4%. Now I put this other surface here at just the right thickness so the reflection is 0. I'd like you now to explain to me how with particles that could possibly occur. Because if the thing comes down and gets, you see, if it either does or doesn't get reflected from the surface, you would say. Well, is you going to say it's reflected or not from that surface? Make up your mind. If this surface is far away, it gets reflected, 4%. So let's suppose it is reflected from this.
How could you have a piece of glass that has only one surface?
Well, the other surface is irregular and far away. What you're trying to do is, if you tilt it at an angle so that the light from it doesn't come to you. Okay.
Photon detector in the glass.
It's off the first
That
surface.
won't quite work, huh?
It's off the first surface.
It's what? Well, I'd say if you put this surface down here at an angle so that the reflection from this surface goes somewhere else, then it's 4%.
Yeah.
If it happens to be exactly that way, it'll add up to 8% because that sends it back too. That's what I should be careful with. But at any rate, the problem is that we would like to say the 8% is 4% from here and 4% from there, and that would be all right, but how are we going to get 0? You say, oh, well, let's make up our mind. What happens at the first surface? Does the light get reflected or doesn't it get reflected? Make up your mind. If it gets reflected, how do you undo it? By putting another surface here. In other words, if that photon is rushing forward, the 4% of 1 out of 25, how is it possible by putting another surface here to turn it to 0, to stop it, huh?
So an absorptive color.
But you're doing it under here. It's already made up its mind to start back. Then you have to rush back and catch up to it and eat it up or something. So you have to haul it back. Where do you have to do something to it too? It's not just getting rid of it, because you find it down here. I forgot to tell you, that's important. Good, it's not absorbed. Because if you put the other photomultiplier here and the one up here, this one is always getting the ones that don't go here. In other words, when this, if you'd ask how many come here and made a plot of that, you'd have 100% of them with that thickness. And then at this thickness, it would be down to 84. And then it would go up to 100 and down to 84. What I'm trying to say is, very simple idea, though it looks mathematical, is the total, that every photon either ends up here or here. Nobody has ever lost, okay? So if you start out by supposing that the front surface reflects the particle, then you can't figure out how you can get the back surface to catch up with it and make it not do it so that you can get a 0 here, or at the next point, and so on. And that's the most cogent argument. It says it can't be little spots, because if it were little spots that would get reflected, then you can't catch it back. As a matter of fact, it's virtually impossible to explain this from the point of view of particles. And Newton went a little bit crazy. I don't mean he was insane. I mean he had very complicated theory for this. He said the following: since the reflection strength depends upon where the back surface is, as you see, it must be reflected from the back surface. But since the amount of reflection depends upon where the front surface is, the degree to which the back surface reflects must depend on where the front surface was. So he proposed the following idea, that as the light comes down, it excites some kind of a disturbance in the glass, so that the back surface, when the disturbance gets to it, it changes the quality of the back surface, so that the back surface will reflect 16% if the disturbance has gotten here just right, or 0, depending on how that disturbance arrived. So he had the theory, it's reflected by the back surface. But the amount of reflection depends upon a condition at the back surface which is affected by some sort of a wave that comes from the front surface to the back surface. Not the light wave, because he didn't have light waves, but a wave of disturbance that the front surface sends to tell it that the photon has just come by here in order to change that number. Rather complicated. He called it fits of reflection and transmission. As you see, what's not reflected is transmitted through. Fits in his language meant chance, as far as I can interpret it. But he didn't, that isn't right either, that it's reflected by the back surface, and if Newton were here, I could have convinced him immediately. But he didn't think of this argument. He didn't think, all his experiments were with 2 surfaces. If you add a 3rd surface, right, then it changes all the things again. With 3 surfaces, even when a place that would have been 0 becomes something. And places that are something are changed. And you can get 0 at some other thicknesses and so on. In other words, the reflection is affected again by a 3rd surface. If it was being reflected at the back surface, how could it ever get to the bottom surface to find out and to be caught and so forth? So we have the same problem between 1 and 2 as we would have between 2 and 3. We can't decide when it's reflected. It can only be reflected on the last surface. How does it ever know which is the last surface? Maybe it's got another one coming up soon. So the whole thing was very difficult. And there has never been a satisfactory model of the very simple process of reflection of light from thin surfaces. Or, in fact, after that, for any other phenomenon. Satisfactory in the old-fashioned classical view. A logical hocus pocus has to be done quantum mechanically in order to describe these things, and that our talk with the boxes was an example of the kind of difficulty. This is another example of the type of difficulty when you try to reason in a straightforward way, in a classical way, about a simple phenomenon.
When there's a third surface, you said it sometimes goes to zero again, but not those same points.
Yes, it just changes that curve to a different one. As a matter of fact, he made one with 32 surfaces, which would also do this. You see, we can't change his thicknesses with his piece of equipment. I've imagined an experimental thing where I can either change the surface or replace one by another, the different thicknesses, okay? We're changing thicknesses. He doesn't change thicknesses. Now, I have 3 surfaces. I got a lot of changes I can make. So I have to plot it in a more complicated way because I have to tell you which thickness I mean that I'm changing and so on. But for every combination of thicknesses, there's a degree of reflection, which can sometimes be 0 if the surface is placed just right for the monochromatic light. And at other times can get up to, with 3 surfaces, 36%. I haven't made a mistake. 12%, 36%. Yeah, right. Yes. A little correction. By this time, the percentage is so high, I have to make a correction for the 96% of 4 business that I was doing before, but it's roughly 36%. So it varies in a similar manner with the 2 different thicknesses. But let's just talk about the 2 surfaces. The 3 surfaces was only to indicate that the ordinary arguments don't work. It depends on all the surfaces, if we had several different materials and different layers. And it cannot be described easily by an ordinary particle picture, and we've gone crazy. I mean, not crazy. I mean, we've had to back up. All we have is a method of figuring out what will happen, which has no mechanism in it. And so what I want to now tell you is what the rules of what we actually do to calculate the probabilities in situations like this. And you'll be horrified. I mean, you're well prepared to be. It's completely without model, all right?
Before you erase all that, what happens if you aluminize the far surface and half silver the upper surface?
It just makes all these numbers stronger. I've only had 4%. A half silver to be something like 50%. And when you have different numbers here, you get curves are stronger. They go higher or come down. And I have to think a minute whether I can get to 0 or I can't get to 0 if this is solidly aluminized. No, because nothing can get through. And it's also all be reflected somehow. But if they were both half silver, you get a curve just like this, but much stronger ups and downs. This only rises to 16%. By the way, if you use water instead of glass, then the numbers aren't 4%, they're somewhat slightly different. Water doesn't reflect quite as well as glass, and I think it's closer to 3 or 2%. I think maybe 2% or something like that, I forget. Okay, same idea though, all right? So now I'm going to tell you how we figure these things out. Because although from the point of view, this is what's most curious. From the point of view of how it works, it's very complicated. You can't get a nice model. It's very difficult. It breaks the head. But the formulas, the rules for computing the probabilities are delightfully simple. The numbers that come out and on the different situations are easy to figure out, as long as you're willing to take arbitrary, crazy rules without knowing what it is. I can give you an example of the situation of a way, but it's not a perfect example. It's just somewhat of an example. The Mayan Indians had a pretty good knowledge of astronomy. They could predict when Venus would appear as a morning star and when it is an evening star, or where they could predict when eclipses would occur and so on. Let's take the example of Venus. In order to do Venus, to figure out when Venus would appear and not appear, they knew what corresponded to a period. It took 584 days to repeat the cycle. That if Venus appeared as a morning star, just appeared on the horizon, then 584 days it would appear in the same place approximately. Okay? So all they had to do was count up the 584-day periods to see when it would come back to where it was before. And this could have been done by making a bowl, putting bowls and counting out every day, taking out one bean and counting the beans. Actually, however, they had developed a much more elaborate method of doing the counting and figuring, which was arithmetic with a number system and algebra, arithmetic. Arithmetic with numbers, and just like we do. We don't count bowls to add numbers. We can add numbers and subtract numbers and figure out what's going to happen without actually taking, if I wanted to subtract 27 from 62, there's two ways of doing it. I put 62 things in a bowl and I take away 27 and I count how many are left. So if I know how to count, I can do additions and subtractions. But if I wanted to subtract 276 from 382, it's too much work. So we have developed techniques for doing that, which in our civilization every kid in school learns. In their civilization, no doubt, every kid did not learn. But this thing. But they had, because I step on this, well, all right. But they had a arithmetic system that the priests knew, okay? And they would be able to predict this because they could count their days and make the subtractions and figure out when Venus was going to appear. So we had a kind of a world in those, probably, it's all in my imagination. I mean, I know what they did because we have some books about it. But I mean, when I say how it looked to them and how many, I don't know whether it was only the priests who knew how to calculate and all. I'm exaggerating a little bit. I tell the story as a model. Then there were these high priests who could predict Venus, and there were people who were the normal man, which we'll imagine said, God, I don't know how they do this. This is marvelous. It frightens me. I can't learn arithmetic. It's impossible, and so forth. Now, if there had been in those days an attempt at pedagogy, in other words, priests trying to explain to the layman what they were doing, they could explain that they were only counting. They were doing the equivalent of counting. Okay? And then explain it. And the guys would say, but there's so much counting to do. It's so much work. Yes, and we made a more efficient way. But don't worry about the more efficient way. You're not going to do it. You only want to know what we're doing. We're just counting beans out of bowls. And we count beans, a certain number of beans, and then we can tell where Venus is going to be. There would be another reaction after you learn that. You'd say, but what is Venus? Why does it take 584 bowls? What are we doing? Was it a rock in the sky, which we think, or is it a goddess coming up, and why does she come up? What do the beans got to do with the Venus? Which is a nice question. Later on, we get this model of a ball in the sky going around with gravity and all this other stuff, but that's for another era. Now, it's very analogous here. I'm going to show you what all the rules of quantum mechanics are, and you're going to say, but why didn't we have to wait until you're a graduate student in school to learn that? It's the same as all they're learning is tricks to make calculations much more efficiently than the way I'm going to show you. I'm going to show you how to make these calculations as if you were taking beans out of pots, okay? It's as easy as that. It's something you'll be able to do. Drawing arrows on a piece of paper according to certain rules and seeing how long the final arrow is the rule I'm going to give you. I assure you that the kids in school who do this don't do it that way, just like the Mayan priests don't actually take the beans out of the bowl, but they're explaining what the effect is that they're trying to do, right? Although they do it with a much more efficient way. So with mathematics and calculus and hokey poke and this and that, there's a way of putting these arrows together that I'm going to explain, but I'm not going to explain that way because we don't have to for our purposes. All you have to see is what they actually do. Then your objection when you're all finished, you say, yeah, that's the way you make the arrows, but what is it that's going on? Which is the analog of, yes, this is the way you move the beans, but what has that got to do with Venus? And the priest says, well, I always predict when it comes, you see, so that's all I know about Venus. That's all I'm going to be able to do. That's it. So knowing that that's where we're going and explaining carefully what I want you to try to understand and what it is hopeless for you to understand, because almost hopeless unless you make a new brilliant discovery that no one else has yet made about how to understand these things. In other words, maybe one of the, and it's quite possible, one of the plebeians of Maya land, after the guy explained about the beans, would think a while and say, ha-ha, Venus must be a rock rolling around in the sky. Right? Maybe.
Or a big bean going around.
Or a big bean, yeah. So maybe you'll figure out it's a big arrow going around in the sky. But it's the same idea. Now, so then with that understanding of what I'm doing, I'm going to explain our rules for doing this. But I'm not going to explain the most efficient mathematical way of making those rules. I'm going to show you the number system and the calculus and all the other botch-watch, which is to do it more efficiently. But here's the way the rules go for this particular situation. And they'll look a little special for glass and so forth. It's a special circumstance. And I'll tell you as we go along more and more generally what the rules are. It's only Wednesday today, and it's possible that I can get to give you the complete system of rules for everything having to do with what we call quantum electrodynamics, but I'm not sure I can get there by Friday. I don't want to rush anything, so we'll just go as far as we can go. Here's the way this works. Here's the way we figure out what the chance is that something happens in a circumstance like this. Just let me tell you, it's crazy, but we're going to end up, all the calculations are done not by counting beans. As a matter of fact, they don't actually do that, but we may. Not by counting beans, but by drawing arrows on a piece of paper, all right? The arrow has nothing to do with the picture, just like the bean has nothing to do. It's not a big bean in the sky. That's the wrong picture. No. The arrows have nothing to do with any of the directions in this. This piece of paper is another piece of paper. It's got nothing to do with the drawing I made over there. It's got nothing to do with the glass. No, it's just a calculation sheet. You go off to the right and start figuring, just like the beans. Nothing to do with beans. What we do is on this piece of paper, we have a center. Maybe if you'd like to put a pair of axes, you might use cross-section paper if you want to be convenient. That's not important. We have an arrow. We calculate an arrow. That is, we make an arrow by some rules, how to make the arrow. That is, we have a pot with a number of beans with some rules about how many beans to put in. Well, we make arrows of a certain size. And when we're done, we interpret the final arrow this way, that the square of the length measures the chance of an event. It goes like this. For every event that you want to ask a question for instance, in our case, the event is a photon leaves here and gets to here. We want to calculate the chance. Then there's a rule for finding a length of an arrow, finding an arrow for that case. And then after this arrow is found, the probability is proportional to the square of it. By the square means the length in whatever units multiplied by itself, or what's equivalent if you have that arrow and you simply built the square on the arrow with all the same side. The area of that square is the probability. All right? Now I have to give you the rules for finding the arrows. And they work like this. When an event, if in this particular case, I'll give you some examples and we'll work out the rules all together, but I'm putting it together slowly. First, for reflection from one surface. The rule for the arrows works like this, that when you reflect from the surface, the front surface, you make an arrow 1/5 of a unit long in this direction. That corresponds to reflection from the surface. The length of it is 1/5 of a unit, 0.2, 1/5 of a unit. If there was only one surface, there's only that arrow, and that's finished. The area of the square, 1/5 by 1/5, is 1/25, or 4%, and that agrees with the experiment. All right. Now, if there are two surfaces, we must make two arrows.
Where'd you get that 1/5?
That's a property of glass. That's a special rule, okay, for glass. I'll come back to how those are calculated much later, when we talk about what glass is, made out of electrons, and how you figure that out. But at the present moment, I want to keep it elementary. I suppose that things have some properties. For glass, it's 1/5. If it were water, I think it's 1/7, approximately, okay? Different lengths for different substances. Let's say for glass, it's very close to 0.25. Now, when we have another surface here, then the rule is for the second surface. For the second surface, it's also 1/5. Nice. Except it's in the opposite direction. It's the same as if it was a front surface, except that when it's a surface from air to glass, you draw the arrow one direction. When it's a surface from glass to air, you draw the arrow in the opposite direction. Right? So that's what you have to remember. Those looked very artificial, those 1/5. They come from the glass. We have to go, later on, we'll get more complete rules by which more details can be worked out from the beginning instead of giving you something. But we're just these two. Now, you would think then if that's right, no, but that's part of the rules. There's one more rule, two more rules. What happens when two things happen? It could either be the front surface or the back surface. Then what you do is well, let me just do it in an opposite order. The next thing, is that if there's a certain distance that the light has to go for monochromatic light, actually that's equivalent to a certain time. I'd rather talk in terms of time. The distance to go from here to here is a certain time. The arrow must be turned depending on how long it goes. Okay? In other words, this 1/5 was what you would have got right here for the reflection. But if you want to know what it would be, that's if, in other words, the photomultiplier were right here. But if the photomultiplier is here, this arrow has to be changed for distance. So when it's changed for distance, this is not an arrow, this is a rule, a change. But how can I do this? A distance does this. The answer is rotate arrow. Actually, for the experiments that we're talking about where the speed is always the same, the distance and the time might be the same. You could either way. And I might make a mistake, sometimes say distance and sometimes say time. They're always proportional for our experiments, almost for our experiments here. It's really time that counts. So let's leave it correctly. It's time. You rotate the arrow at a certain rate, a certain number of rotations for every second. Okay? You rotate the arrow around. So, for example, if the time is short, very short, this arrow, if the photomultiplier is not exactly at this surface but just back a little bit, then the arrow would be slightly tilted. If the photomultiplier were further back, still it would be tilted more. Angle would be increased. In fact, the angle is simply proportional to how far it is away. It's like a clock, in fact. You could imagine it as the hand of a clock, which is, except I've made it go backwards, right? I mean, clocks usually go the other way. It's the hand of a clock, which is measuring how long it is to get to here. And it goes around as it gets to here, all right? Actually, for any reasonable distances, this is a very large number of turns. It turns once every, for yellow light, something like 25, well, you talked about it before, 40 millionths of an inch, but that's an even shorter time. How long does it take light to go 41 millionths of an inch, going at 186,000 miles a second? That's the amount of time it takes to turn that once, okay? Each time, for each 40 millionth of an inch of light time, this thing is turning once, so it's going around pretty...
One wavelength?
Yes, that's exactly what, precisely.
Sodium lights are about 5,000 amps.
Yes, yes. Which I was saying is 41 millionths of an inch, I think, if I haven't made a mistake in arithmetic.
500 nanometers.
But the time is very short to go that distance, and that's the time I'm talking about, okay? Now, we have, of course, let's suppose that the first arrow, as a result of having a photomultiplier 16 miles away, or 16 centimeters, that this is turned 1.5 billion times around and it ends up here, okay? Now what would happen to this arrow? I'm sorry, I made an error. I should be the total time from when it left here to here to here, okay? So excuse me, it's the total time that turns, how much you have to turn it. Now this time, when I go from here to the back surface in here, I also have to turn it by the total time. So this arrow has to also be turned by a very large time. But they're not equal. They're not equal because the total time to come down to here and come back to there would be longer than to go from here to here. So this one is turned more than the other, if there's any thickness in here. So let's say it's very thin, then it's only turned a little bit more. Let me take the case that it's turned just a little bit more. Then this arrow, if it were turned exactly the same amount as this has gone rotated 6 billion times and a half. This would be rotated 6 billion times and a half and would come out there. That's the way it would look if the times were exactly equal, right? Because they were opposite to start with, and if they both keep turning the same amount, they'd always stay opposite. However, this turns a little bit further depending on the thickness, and therefore, in fact, this is not really what it is. It's more like that. Okay? All right. So far, we haven't computed anything, just found the arrow with 2 arrows. Now, the situation, the rules go, I'm just developing them in this example, and we'll develop them as we go along. The special rule about the 1/5 was special for glass. The speed of turning is special for the color. a different color turns more rapidly per second. But the more important and general rule that I'm about to mention is how you put together something can happen in more than one way. We have a situation here in which we say, when we get the light here, we could say, it's either reflected from the front surface or the back surface. I taught you not to say things like that. If you're not observed it, don't say either. Either in the sense of calculating arrows. It's a situation in which there's a way that you could think of it as happening, and there's another way that you can think of it as happening. For each one, we have an arrow. We now have arrows for these two ways. Finally, I must tell you what the arrow is for the net result. When things can happen in alternative ways, you do what we call add the arrows, and it doesn't mean anything. How do you add arrows? I know how to add numbers. How do you add arrows? The rule for adding arrows is the following. You simply put one arrow head on the tail of the other. If I wanted to add these two arrows, I would do it as follows. This is the first arrow. Let's say that's 1 and that's 2. That's the first arrow. And then I just draw the second arrow off from the first one. Okay? It's exactly parallel. So drawing the same, but it's centered, is moved to there, right? You tie one onto the other, head to tail. And the result is supposed to be the sum. The adding is this net arrow that you would get from where you started to where you ended. A way of thinking of it that's rather nice is to think of each arrow as indicating the direction of a step to be taken. We take a step on this plane this way, and then we take a step that way, and we say, where did we actually move? We could have done it all in one step, this one. So this is the one step which is equivalent to the succession of the other steps. Adding means putting together steps, thinking of these arrows as steps that you do in succession. This added arrow is the final result for the chance of a reflection. The square of this arrow determines the probability of reflection. I have to have erased the blackboard because I haven't got room. So I'm reconstructing here on a smaller scale a diagram that we had made earlier, which was the reflection as a function of thickness, which I'm trying to explain. And this is up to 16%, remember? Averaged 8% and started at 0. Now let me explain why it's true, if I follow these dippy rules.
This must require an incredible accuracy of measurement.
Not particularly. Not this one.
I mean, timing here.
Oh, no, but you see the timing is automatically taken care of by just the distances. The timing is very short. But
The distance.
well, we have to have the distances good, yes, but you see, if this is put in a fixed position, it's a definite distance, whatever it is. We don't actually have to know exactly how this is turned. We have to know the relative turn of this and that. That's a nice point. Suppose that I made a mistake in that distance. Well, I moved the photomultiplier a little bit further away. Then this arrow here, the red's going to indicate what I would calculate if I had a little further away the photomultiplier. Then this arrow would have turned a little further, right? And this arrow would have turned a little further, always in the same direction. Yes? And now I want to add these two together, which I will do, again, just like I turned blue to black, I'll turn red to orange. I'm going to add the red ones. It's a new problem. He moved the photomultiplier on me, and I'm doing it over. So I make this step, and then I make this step, okay? And then I get the final result, which we'll draw in purple, that corresponds to the other green one there. And it looks like it's the same size, doesn't it? Maybe I cheated, I'm good at drawing. But it is exactly the same size, because if you think about it a little while, since you turn this arrow by a certain extra angle, and this one by the same amount extra, because when you move the photomultiplier, the extra time is the same for both, the extra time. So the extra turn is the same for both. It's the same as just turning both arrows together, which is simply turning this diagram. But turning this thing doesn't change its length. And the probability that we're calculating depends only on the length. It's the square of the length. It doesn't depend on the direction.
Can't you get that directly from the glass thickness? From the glass to the glass?
Absolutely. You mean that this angle here, this delay? Yes, yes, and we're going to do that right now. And that's exactly right. That's why you don't need the accurate measurement that you were talking about. You don't really need that distance to get this probability because...
The thickness of the glass is uniform.
Only the thickness of the glass is important in computing the length of this arrow. The direction of this arrow does in fact depend upon exactly where the photomultiplier is, but it doesn't affect the probability that you'll get a count, because the count is measured by the length of this arrow squared. Right?
So it's the scalar, not the vector.
No, because I need this. Sometimes I might have 3 surfaces and I may not have a photomultiplier there, but when I get there I have another surface that a light reflects from and so on, so let me have it with arrows. But when you finally want the probability for something, then at the end you square the arrow. For this application, it's the same answer here as here. Okay? But if I had, instead of putting a photomultiplier there, I had put another surface there, then the exact location of it becomes very important. Okay? I had another reflection with another photomultiplier somewhere else. It would be a different problem. But let's just do this easy problem first. Let me explain why this result would occur if these rules were right. Why, if we count the beans by this way, we get this result. Let me show you, all right? He's already seen it, as a matter of fact, from his questions. Suppose that we would do the problem over again, not this time moving the photomultiplier, which we found out was an effect, didn't change anything. So I'm going to erase the red and orange to get space. I'm now going to ask you to think of another circumstance in which I change the thickness of the glass by increasing it, let us say, a little bit. So I do the experiment over again, and now my red and orange and all that's going to correspond to thicker glass. To make it very clear, I was going to do it over again in which the back end of the glass is here instead of where it was before. What happens? The amplitude, well, I mean the arrows are called amplitudes, so I may sometimes say amplitude instead of arrow. That's just a word, right? We can have any word we want, like it says in Lewis and Carroll. Lewis Carroll, I mean. The reflection from the amplitude corresponding to reflection from the first surface is this arrow turned by the distance to the photomultiplier, which is that. Changing the position of the second surface has no effect on that arrow or that amplitude. Instead, however, the one which went down to the new surface and back is changed. Why? Because it has to go further now. And in going further, it will be turned more. So it will be in this position instead of where it was before. This corresponds to turned more because it's thicker. This is the one that's thicker. All right? Now we have to put these 2 arrows together, and I'll do that over here. The black one for the old one, which is the same as it was before, straight up and down. That happened accidentally for my drawing. And then this red one, which is now, I'll draw in red again. I don't want to change all the colors all the time. Out this way more, right? You can see it. I'm trying to draw it parallel. Just like I drew this black one parallel, I'm drawing that one. I'm making the 2 steps again. But this is the first step this time, and this is the second step for the new experiment. So there's a first step and second step for the new experiment. The result in this new case is the new green arrow. I got so many colors and I have so many possibilities, it would be sensible to put the right color caps back on them in case I want to get the right color. But I can't resist having every color in the rainbow on this diagram, but I don't know that it helps any. At any rate, we have this green arrow here. You'll notice it's longer. And why is it longer? Because this angle opening is greater. So it's longer, and being longer, its square is greater. And the probability of reflection, then in the new situation, should be larger. The probability of reflection will depend upon the thickness of the glass. And in this particular example, this may have been the first point, and this may be the second point. That is, it increased as we increased the thickness. That's how it works. Simple as long as you believe all this, that it'll work. I mean, yes, it is simple. It's just drawing arrows.
Configuration of the arrows to once again produce the thickness, where you keep increasing the thickness till you get 0 reflection.
We'll see that in just a second. I just want to see if there's any other question. I'll answer that. We're going to do all the different thicknesses and get this whole curve now.
But that's exactly what the wave theory tells you.
Of course, because the wave theory gives the right answer too. But the wave theory doesn't give the counts. It doesn't calculate probabilities. This is for calculating probabilities.
You just rename the ordinate. You call it, instead of reflectance, probability of reflection.
It's not just a name. Because when we measure probabilities. We measure average rates. We can't get a quarter of a photon. Yes, the mathematics is exactly the same as the wave because it's very simple mathematics, but it doesn't mean the wave theory is right because it predicts wrong things about the photomultipliers, for example, that it's counting, that it's chance. It's a very important difference. It's not the photon, the wave theory would have the waves there weak at the photomultiplier, but what the wave is, what is it? It's supposed to be energy. No, it's probability. A wave of probability? Yes, that's what. Okay?
No, I mean, we get to the dual slit later, which...
It doesn't have the dual slit right now.
I mean,
We have what you call the dual slit. He knows too much, see?
So the problem is...
We have to undo some of your lumber that we talked about.
How does it happen if the two photons go up?
There's no two photons.
Well, I mean,
It's one photon.
and then they hit together,
There's no two photons. There's one photon. And it's either there or there, and we're trying to find out the chance it's here and the chance it's there. That's very important. I want you to get used to it.
I know, but I mean, it's still, it's not...
The same mathematics as the wave equation. The mathematics is the same, but instead of calculating what you call the intensity, you're computing the probability of finding a photon. The fact that you made this change of interpretation means that the pictures of the waves is physically incorrect. Okay, so we remove the picture and just make the calculation. That's what happened. We're not going to change the calculation because the other numbers were right.
In the direction of flight, how long is a photon in terms of wavelength?
In this particular example, when it's monochromatic, it's infinitely long, but that kind of question is the kind of question we were talking about. If you try to make the model too correct, it isn't going to be right for some other question. Just sit down, just follow the arrows, and then you'll get everything right.
How could it be an infinite length? Could it then be an infinite duration?
That's right. And if it isn't infinite duration, it's not perfectly monochromatic. But if it's nearly monochromatic,
Infinite cube.
these are irrelevancies, please. Okay? They're not really irrelevancies in the greatest delicacy, but everybody isn't up to your level of worrying about this particular problem, which is not...
Worrying about the duration of the excitation of the photomultiplier by one photon.
I know. It's an unnecessary complication to worry about that here at the present time. Okay?
Yes, it was.
Okay, fine. What I would like to do now is get this whole curve from this to see how it really works. So let's start by taking the case that the glass is very, very thin. Very thin. Then the two times are the same. Let us keep the photomultiplier here and the front surface exactly here, so that in every example the front surface arrow is this one. And now let's figure out what the back surface arrow is in different cases. And we'll find these pictures coming out like this. I should have used a different color here so you'd know this was the back surface arrow, okay? Here's our front surface arrow. I'll make it larger so you can see it better. Shouldn't have done that. I should have left the scale exactly the same. Yes, I shall do that. It's not, we change too many things, you get mixed up, and there's no need to change. There's the first arrow. That's supposed to be that one. Now on top of that one, I have to add, by the other step, the second one. Let me draw the second one. This was a small thickness. This was thicker, some thickness. We'll call this thick, thicker, and very thin. Where's very thin? We noticed that this was very close to here. They both turn the same amount. And since they started opposite, very thin would be here. That would be where it would be for very thin. I'm drawing them all on top of each other. Of course, they're all separate calculations for separate experiments, and it's a little confusing. So let's just draw it all over again for the case that it's very thin. This would look like this. Same again. This one, however, would be exactly opposite. Why? Because if it's zero thickness, there's no difference in time for the front surface and the back surface. Therefore, they both turned around 1.5 billion rotations. This is a half a rotation extra net, and this is a half a rotation extra net, therefore upside down. Now let's put these two steps together. First, we have the first step for the first arrow, and now we have the second step for the second arrow, which is a step back. Although I've drawn it to one side so that you can see it, it should be tied right onto there. And where do we end up? we end up right here. So let me draw it very carefully. Actually, I made it for the case that there's a tiny thickness so you can see it. Then you see that the green arrow is at virtually nothing. In fact, it is 0. If it was exactly opposite, the net result of making a forward step followed by a backward step is to bring you right back where you were, is no net motion. And therefore, there's no probability of getting a reflection. That's why a very thin piece, I mean, that's in consonance with the experiment, it says that a very thin layer gives nothing. Now, okay, now we keep on going, and we try to imagine what happens as it gets thicker. All that's happening is that this arrow goes around and comes to here and then goes back down and goes around and so on relative to the first one. So you've answered your question. You imagine what happens if you take an arrow here and then for different thicknesses, and I'm going to draw it all for a succession. I'm now going to draw the result for 16 experiments in which I go here, 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 here with different thicknesses, okay? The 16 results look like this. Maybe it isn't going to come out 16, huh? That's no thickness. There's a little thicker. A little more time, the case we drew before. Still thicker. These are not straight lines, unfortunately. They should be. They're a little thicker, a little thicker, a little thicker, a little thicker. That's more turn, right? These are the way these things come until finally, when the thickness is just right, it's turned one whole extra revolution because of the extra time. Then it's back to this case, and it keeps going around. And how long is the green arrow? Well, the green arrow starts at 0, and then it gets a little bigger, and it gets bigger, it gets bigger for the different cases. And finally, it's way up this way. That's the biggest it's ever going to get. Then it comes down again. There's a bump, 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 right? And how high is it at the biggest? You may have forgotten, the original length was 1/5. And this is obviously 2/5. And when you square 2/5, 2/5 is hard to square for anybody. It's 4/25, which is equal to 16/100. Or another way, 2/5 is 4/10. This is 2/10. Squaring it is 4/100, which is 4%. Twice it is 4/10. Squaring is 16/100, which is 16%, which is okay. And that's how it works. It goes up to 16, comes down, and so forth, depending upon how thick the glass is. And this will keep on going as you keep on making the glass thicker and thicker. It's been measured to, I said, something like tens or hundreds of millions of rotations.
Is this independent of the index of refraction of the glass?
No. The time to light to go through glass is different than the time to go through air. It goes through the glass slower and takes longer to go the same distance as it would for air. So that when I calculate this turn, I had to allow that when I'm calculating this extra time, I must be careful to realize that it's not going at the full speed in the glass, but slower. So that's just to change those angles, but doesn't change the result that I got in the picture. Okay?
That's why you said earlier that you should pay attention to the time rather than the distance.
No, I just like to pay attention to the time rather than... Well, no, it's okay. It's not why I said it. Yeah, okay, why I said it. If you pay attention to the time, then and say the rule is for time, and allow that the light goes at a different speed through the glass, that explains it. Okay? Later on, if we get there, don't know if we can make it, but I will go further. I will explain why light goes at a different speed through the glass. I will actually improve this thing. I'll give you more details of how this calculation actually goes. I've cheated a certain bit because this is a result of a more complicated calculation that determines that this is 1/5. It's a result of a more complicated calculation with arrows that determines as you go through glass the speed at which you're supposed to rotate is different, and so forth. These I haven't included, but I made it supposed a certain number of things. But those things also can be explained by a finer analysis of the arrows, all right? Including the minus sign for the back surface. Yes, I'll explain. All those will be explained, I hope, if we get there, by a finer set of rules, a more detailed set. We'll just take these as properties of glass at the moment.
But if it's still, if it's still better to use the analogy that, you're traveling.
Yes.
On land, you use a car.
Yes.
On water, you use a ship.
Yes.
are different. And, I mean, on things like this, you know, you just have to use wave theory in all respects, including, you know, total refraction, lateral waves. It gets very complicated, where you have to, I mean, the only guiding thing is wave theory.
No, sir.
But you can't think.
No, sir. That's incorrect, sir.
Convince you that there's an alternate.
That this is the way to do it.
Well, but this, I mean,
At this level, it looks like wave theory. You forget that you're computing probabilities. That's not right, according to wave theory. And we'll show you circumstances in which the wave theory doesn't work. We had one with the two boxes. If you have problems in which you have two photons, which are correlated in their properties, the wave theory is unsuccessful.
yeah, but it doesn't help me. It only
Doesn't help you to do this, you mean.
problem as soon as I put a quantum multiplier there, because that works by the
But you haven't done any problems with two photons that are correlated. That's nonlinear optics problems, for
I'm
example.
having a problem in
You haven't done them, therefore you don't appreciate. Okay, so because you have a limited range of experience in which you work, you might find that some other model is sufficiently successful that you don't have to do it this way. What I'm trying to show you is a model which works, ultimately, over the entire range of experience that man has been able to find, not just over the limited range of experience for your particular experiments, okay? It has always been this way, that for a particular range of experiments, a certain idea may be a good enough approximation and complete enough, because you don't do those experiments which get you into trouble with it. And then it may be much easier on the head, if you like, to use that model. It's much more easy to imagine the waves moving in space and so on. But you will, if you wanted to do a wider range of experiment, get into trouble if you perpetually thought that way, I guarantee you.
But still,
Whoa,
I mean,
that
you're
sounds
starting
pretty
out by
heavy.
saying that what you have today, you know, might be changed tomorrow.
That's true, because we have no experiment.
So the current universal model
Right.
is only a temporary model.
Perhaps.
And so,
But why do I go back to your temporary model, which I know is wrong in certain circumstances?
long as I know where to use it, where not.
That's perfectly all right, sure. But that's not what I'm lecturing about. I'm lecturing about the physical view over a wider range than your particular experiences. And so I want to tell all that we know, not some approximation which works in part of nature, okay? So that's the reason I'm
Also,
doing
there's
it.
something else that's very important, which is to prove that this sort of crazy way of looking at it reproduces all your results perfectly well, which is what you have to do when you invent a new theory.
We have to show that it produces some results that he doesn't know about, too, such as the two photon correlations that were those boxes in the beginning.
Well, then you get into line spectra and all kinds of things that the wave theory falls on.
There's lots of difficulties with it. It's got mostly to do with probabilities. That you can't interpret the wave as a probability. And all it really is that the wave is interpreted as a probability instead of as an intensity in first approximation with one photon. When there are photon correlations, it has to be done with arrows. Okay?
A little stretch.
Sure.
Is that okay now?
Well, of course.
Yeah, I like a stretch. Yeah, like there's a staff that can possibly do that.
So you say your wave probability in a sea of arrows?
Yes. Right. If we have more surfaces, well, let's see, what should I describe next? We appreciate the plus. No. I would like to talk about what happens if there are more surfaces. All right? If there are more surfaces. For example, if I had a layer of glass here and then of air, much like you like to make, and then we would have another layer of, let's say, glass of a certain thickness, something like that. Maybe not the same thickness as this one. Well, let's erase the red line to make the picture a little easier. We have thicknesses, 4 of them. Then what happens is that we would make 4 ways that the light could go, if you imagined it. You could say it goes first surface, second surface, third surface, and fourth surface. And then we would have an arrow for the first surface case, an arrow for the second. If these were different materials, they weren't both glass, they may not be the same length of arrow. Some other arrow for the third, excuse me, I made it wrong. An arrow from the first surface, an arrow from the second surface, another arrow, let's say it's bigger, let's say it's thicker glass, different kind of glass, lead glass, so it's not 1/5, it's a little bit bigger. This is the third surface, and this might be the fourth surface. How do you put them together? You consider them, you add them, again with the word add. We use the word add, but what we mean is we find out what the net result would be of this sequence of steps. In other words, we try to find out where we would end up if we made a series of steps, this step followed by that step, followed by that step. And the easy way to do that geometrically is to draw one and then draw the next one on the end of that. That's number 2. And then number 3 on that. I didn't draw it quite at the right correct angle. And then number 4. And then the net result for the probability would be the square of this length. In other words, the area of a square set on that arrowhead. That would be the answer. So when we have any numbers of surfaces, all we do is figure out the arrow corresponding to each one and tie them together by what we call addition, which is really seeing what happens if you do a sequence of steps corresponding to those arrows in succession. An interesting point about adding, which is fun, with numbers it's true that 5 plus 4 is the same as 4 plus 5, and it doesn't make any difference in what order I add them. If you play with this a little bit, you'll discover that if you make a series of steps of different lengths and angles, you'll get to exactly the same place with no matter what order you make the steps in. If you make a big step this way, followed by a small step that way, you get to here. Whereas if I made a small step that way first, and then the big step, I get to the same place. And it'll turn out, if you play a little bit, that if you tied arrows on each other's ends, but kept the same arrows, but tied them in different order, it'll come to the same answer. So this addition also has that property. It doesn't make any difference. You don't have to decide which is first and which is second when you're adding these things together, okay? You just put them together, and it'll work whichever order you choose. Now I would like to describe the language we use to describe this, right? We call the arrows, actually, a physicist calls an arrow an amplitude. He actually more completely sometimes calls a probability amplitude. All it means is a quantity, which one squared, or rather which one you find the area of the square corresponding to the arrow, is a probability. The word probability amplitude is just, I could have better say probability arrow. What I mean is that you use the arrow to find the probability by figuring out how big an area of a square on it is. So these could be called probability arrows. Actually, technically, these arrows are called amplitudes. It's just another word for these arrows, right? No complication. I would like to use the word amplitude because I'm so used to it. It probably would be easier for me to say the probability arrow associated with this rather than the amplitude associated with it. But I'm used to using amplitude, and we might hear the word somewhere else, and now you'll know what it means. So what we do is this.
That includes angle.
Yes, the amplitude is a...
It's not the scalar, it's the...
No, it's not the area, that's the probability. The amplitude is the arrow with its angle and length, the combination. That's the amplitude. It's the full arrow. It's got 2 aspects, the length and the angle. That's the amplitude. Amplitude and arrow is the same, all right? Just get used to that. Now, we have discovered from our experience with the boxes and also from talking about this, that it will not work out right, and we'll get into all kinds of trouble if we would say something like this, that this particle, in the classical sense, that this photon has a certain, comes down to here. There's several ways it can get to here. It can come from this surface, or it can come from this surface. There's a certain probability to bounce from this one, and a probability for the bounce from that one. That will not. We've noticed that, because if there were a probability to bounce from the front surface and the probability to bounce from the second surface, if you added those probabilities together, you couldn't get 0, as you sometimes get for certain thicknesses, because all probabilities are always plus. So that theory, that way of describing that we say the photon probably does this or that, is much like with our boxes, that they're probably red, red, green, or green, red, red, or whatever they are before we open the box. In other words, before the photomultiplier reads, we cannot say, we do not say, that this photon either goes this way or that way or this way. But we do say, following language, it has an amplitude to go this way. It has an amplitude to go from the second surface, has an amplitude to go from the third surface, has an amplitude to go to the fourth surface. Then you add the amplitudes together to get the amplitude to arrive here. The amplitude to arrive here has only meaning in the sense of the probability of arriving here, which is the square of the length of the amplitude arrow. So, to say it again, every event that we want to calculate, we calculate a probability. These probabilities are always the square lengths, the area of the squares, associated with arrows, translation, associated with amplitudes. For every process, we compute an amplitude for that process. The probability of that process is the square of the amplitude, the square going on the arrow, right? The amplitude for a process which can happen in several alternative ways in your imagination is simply the sum of the amplitudes for each of the individual waves. In other words, the arrows, total arrow is the sum of the arrows for each of the waves. So that it turns out with this happy way that we can blithely go along and thinking of it happening as alternative different ways, but not in the probabilistic sense, but that in the amplitude sense. There's an amplitude for it to happen in all these ways, and we have to add those amplitudes. That permits cancellations and so forth. Arrows, when they add, can come out zero. Probabilities can't. You can't add two positive numbers, two chances, and get nothing. So, but with arrows you can. So the language we use is to say that there's amplitudes for different possibilities, and to find out whether it's actually happening, with what chance it happens, we have to, in the end, when we know the amplitude, find the square area that belongs to that amplitude, that arrow. Right?
That square area has no direction, right?
No, it's just a way of my describing just squaring the length. It's a numerical process. They don't have to draw that square, but for people who don't want to calculate, I just draw the square to indicate the bigger the square, the bigger the probability. If the arrow, like, and an example of that, why it's nice to draw the squares so you don't have to calculate anything, is remember this last one where we had the full maximum corresponding to this position here. Then we had an arrow this long, which was 2 units. Twice as long as the original one alone would have been. Twice as long as the first surface. If it were the first surface alone, it would have been so big, but it's not, it's twice as big. Now if we draw a square on it, and compare that to the square from the first surface alone, with a little bit of drawing, we can see that there's 4 of these squares, and therefore it's 4 times more. So for individuals who can't square numbers easily in their head, I've shown you that the double arrow has 4 times the probability than the single arrow, because the probability is the area of the squares. And so therefore, when we had the 2 surfaces so lined up that their arrows were in what we call in phase, that is in the same direction. Phase and direction or angle of the arrow is the same thing, just other word. When they're in the same phase and they go that way and they add together, then the probability is 4 times as big as one would have been alone. That's why 16% is what happens rather than 4%. All right? I was just drawing squares to help you to calculate squares. If you're used to multiplying numbers together, then you can just take the length of the arrow and multiply it by itself. In fact, I did that in this case over here. I forgot that I had invented this square to save me from having to multiply numbers. So I've got it down to the point of counting beans to the last degree, that you don't even have to multiply numbers in order to find the answers to this. It's a geometrical square. Okay? So that's the language we find ourselves using. We talk about amplitudes for possibilities. If I were talking about those 2 boxes in a more sophisticated way, I'd say there's a certain amplitude that the combination is red, green, green. Another amplitude that it's red, red, red. And I talk about adding those 2 possibilities, not by adding their chances, but by adding the amplitudes for each, those 2 arrows together. And that's the way I can get funny numbers that are not what you'd think you'd get with probability. Yes?
I think maybe what John was worried about a little bit in that earlier question
Yes.
is just that a probability is always a number between 0
And 1.
Between 0 and 1.
Yes.
And it looks like you'd have an arrow of any size and you square it and get any number.
Actually, you can't. These arrows are small enough that when you put them together, you can't get any number.
Yeah.
It's true. You mean if I made enough surfaces and had them lined up perfectly, you'd say, why not? Look, there's 0.5 for each surface. So let's make 10 surfaces. And let's put their position such that the timing is such that all these arrows line up. Then we'll get more than 1. The thing will be probably more than 1. That's because I made a mistake or an approximation. I disregarded the situation, the fact, and I'll explain later more correctly how to do this right. I made a little bit of an approximation. I assumed that what happened on the back surface, that the light that got to the back surface was not already affected by the front surface and so on. We'll come back and explain how to straighten that out later, okay? In fact, I can do it now. Why not? Where I've simplified this discussion, and we can even see that in two surfaces I've simplified it, there's a slightly more complicated. I've left some stuff out in order to get the rules straight by making it simpler for you, by leaving something out. What I've left out is this. Not quite prepared. I have to go back to my room and check numbers and see how to explain it quickly, but I'm going to explain the problem. There's several ways that this light could get here. One of the ways is to go to this surface and come to here. That's one end. Another way is to go to this surface and come to here. But there's still another way. Can you imagine what it is? Yes. It could go to this surface, then to that surface, then to this surface, and then back to here. That's another little arrow that has to be added on. This is incomplete. There's not just two. There's another one. It turns out that one's particularly small. I'll explain the rules for finding those later. They get very small. They're very small. It could, of course, come down, hit here, go up here, go up here, go back, and go back, but then go up here. So there's a lot of little pieces that I left out. Now, when you have these 5 surfaces in which you're trying to line that up and make it very much bigger, then all those other new possibilities are also enhanced in such a way that they add up and screw you up so that you don't get more than 100%. The details will be presented next time when I have a chance to lay it out in a simple way. I don't want to confuse it by screwing up while I'm trying to explain it, okay? But there are these other possibilities which we've neglected in this discussion. Yes, I would like to do one other phenomenon that you're familiar with by arrows instead of the standard way of doing it. This phenomenon will bother you still more because it's much easier to understand by common sense. Nevertheless, the problem is this. With these rules of arrows, which is something new, how can we understand everything that we understood before in a different way? In other words, when we have a system of rules, we can't use one rule for one case and another rule for another case. We'd like to see how this kind of rule analysis works always, even though there might be an easy way to guess the answer from a different point of view. I want to show how this consistent point of view produces all results. And the results I'm going to show now, next, are very simple ones, which you would certainly believe and see in a much simpler way. So why do this? Why we do this, I'm trying to show you how this particular theory is the universal theory under everything. It'll produce even the phenomena you're used to, as well as esoteric ones. It does them all. The phenomena you're used to can be explained much more easily by some model, but that model will not hold up if we extend the array of phenomena we want to observe. This, however, holds up over the entire range, familiar and unfamiliar. So, the familiar one that I want to discuss is reflection of light from a mirror. And that's easy. So, we have here a mirror. In fact, this mirror could have been one surface of glass, if you want, right? That's a partial mirror, but it doesn't make any difference. So let's take a mirror, and here's the mirror surface. If I shine light straight down and back, we've already talked about an amplitude that it gets sent back, which is 1/5 for the surface of glass. And if you make it a good mirror, that 1/5 gets to be 1 from the surface. If you make it perfect, it would be 1, yes.
That's a theoretical mirror.
Yes. Now, however, the thing I want to change now is instead of thinking of the light and the situation and the geometry only up and down, I want to think this is a really two-dimensional world. Our source is over here, and our detector is over here. All right? And now I'm going to try to calculate the chance of getting light over there. But what I want ultimately to understand is what everybody knows, is that the light goes, it hits the mirror and goes to there such that the angles are equal. It goes, the light goes this way and then comes to here such the angles are equal. I never made a rule about angles being equal. I talked about arrows. Where the hell are the angles equal? Now I show you, all right? Magic way in which the arrows produce this result. You know what I'm talking about. If for this example, if your eye was here, you would see this in the mirror at this location. Actually, it would appear to be back here, the optical effect. It appears to be an image appears over here, which is simply the same distance behind the mirror as the actual object is in front. So the eye looking at it sees it here as if the light came from here, but actually it comes from there. And if you figure it out, this angle equals this. Reason is, by the way, if you remember your elementary geometry, that if you were to draw it to that image, not the reason is, but imaging works because, you see, when you have elementary geometry, these two lines make the same angle coming this way as they do going out the other way. This angle here is the same as that. But because of the way I've drawn this symmetrically, this angle here is also the same as that. And these two are equal. That's the standard description. It doesn't look very equal on my drawings, but that's supposed to be equal. Now I would like to explain why that is, okay, from this point of view of arrowing. So I'm going to try to discuss this. And here's how you say, why does it go only there? Well, it's very amusing and very interesting to see how it works. I'm going to do it this way. I'm going to suppose the light goes straight through the air. We'll later discover even that can be explained. We've been assuming that, but we'll take that. But let's suppose we don't know that light has to be reflected here. And we would just say, for purposes of analysis, that we divide this mirror into very tiny sections, little pieces of mirror, okay? Bip, 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 just to think. The smaller you do it, the more accurate your result will be. This is small enough for us. And it goes on, although I don't want to draw. All right. So I want to think of this. I'm going to say, and it's going to be right, what I'm going to say, that actually there's an amplitude to arrive here. I'm going to calculate the amplitude that a photon arrives, which you can do in many ways. One way that the photon may have gotten there is to go down this way and go across to here. Right? Not very likely. I know it's equal angle. Shut up. It's possible. It doesn't know anything about that. Another way, I'll draw in purple so you can see it's another way. It could have gone to another spot and gone to there. It's still not the right thing. It could go to still another spot. I love these colors. Let's say it goes to the spot way over here and goes to the photomultiplier. Yeah, right. And by the way, there's still another way it could go. It could go straight to here without going to the mirror at all. That produces very funny effects, as a matter of fact, but we'll put a wall in here or something to stop that light. So let's imagine that this is specially built, that there's a wall in here, so that we don't have to consider the light that doesn't hit the mirror, all right? This, of course, was one of those spots. Because of my laziness, I haven't drawn enough of these dots in here. Now,
Is this a point source?
yeah, and a point, it's a very tiny detector. There is the one we're looking for. Let's say this is the one of equal angles. That's in there too. That's this one. All different, well, I'm sorry, I shouldn't have bent that line. Okay, let's say that there's this one. That's the right one, we'll suppose. Okay? But every one of them is there, and every one contributes an amplitude, a small amplitude because it's a very tiny section, a little tiny arrow. And I'm going to add all the arrows together, and I'm going to show you, like a magician, how it works, how the mirror works. I'm going to add every one of these cases. Each is equal. Each one of these things is the same width, and although the distances are varying somewhat, they're almost equal in their contributions. Every one of these is equally important. So let's start to draw the arrow. I draw the arrow for this one, a tiny little arrow, at some particular crazy angle that depends upon the total time to go from here to here. In fact, just for fun, well, no, it's too silly to draw the blue one and the purple one and the black one as arrows. But, okay, the blue one is going to look like this, see, the arrow contribution from the blue one. Now the purple one has about the same width and some slight difference in distances, and I'll give you the rules for those arrows, but it comes out almost the same size. However, the time is very different, because the time it takes to go from here to here and the time it takes to go from here to here are not the same, because if you count, well, let's take, it's perfectly clear that this distance total is longer than that distance, for instance. They're different distances. Therefore, they're different times. So all these arrows that I'm going to draw, the purple one, the black one, and the green one, they all correspond to arrows in some crazy directions, depending upon the time, all right? And I have to put them all on top of each other. Not just these, I also have to put all the ones in between. Okay, so it's a big calculation, adding thousands of arrows together by tying them one to the other. Remember how to do it. You make the succession of steps. Then, okay, now we're going to do that. I hope I have time. Yes, I do have time. We're going to do that. In order to do that, we have to know at what angle to turn the arrows. That angle is the total time taken to go. And the total time taken to go is, of course, the distance divided by the speed of light. And so what I need for each of the arrows is an arrow associated with this spot, this spot, this spot, this spot, this spot, and so on. In order to figure out at what angle to draw it, I have to know how long it takes or how far it is. Okay? So let me make a little diagram or a plot, a graph of how much distance it is, or time. It's the same for us because it's all through air. And it's going this way. And this axis is supposed to really be exactly corresponding to each one of these. In other words, for this particular spot here, I calculate the distances there. For this particular spot here, I should do it in purple, but it takes too long to keep picking up the different colors. So this one here, turns out is somewhat shorter. This one here, maybe even shorter. After a while, it's getting long again. As a matter of fact, you can appreciate the one that goes straight down, and if this is there's some kind of symmetry, if I happen to have them at the same level, that there'd be some symmetry, go up again. At any rate, the distances, or the time, which is equivalent, because we haven't said what the scale is on the axis, there's a curve which goes down to some lowest value and goes up. Unlike my drawing, they should have gone through these dots, so I should have put those dots there, moved the dots. But you know what this means then, and these are a whole lot of little dots corresponding to the time for each of these places. And there's some place in the middle there somewhere where the time is shortest, and then it begins to increase again. Are there any questions about what that curve is and why it looks that way? Because it's important to appreciate that.
I'm not sure where you're getting the distances from. What does that first point
Good.
correspond to?
This point corresponds simply to the total of this length and that length. The total distance to go from here to here and from here to here.
So it's a summation of...
All it is a summation of those two lines. As a matter of fact, it could be constructed geometrically that way. You can go home tonight and draw a horizontal and 2 points, and on the horizontal lay out dots and draw these things and then lay them out, measure them, and then measure this height here should be equal to the total of these two blues. Actually, I don't have room to draw, so the scale is different. Okay? And you'll discover that there's some distance at which the time is shortest, and then it goes up again. The only thing that really counts in this curve for us are the dots, one corresponding to each one of these little sections. Of course, we can make the sections very fine, have lots and lots of dots if you want to. Now,
Is that a little piece of that other curve that you did, the big up and down curve?
no, this is entirely different because we're plotting something else. We're plotting the distance to go at different points, and that's not to do with the intensity of light from the other. It's a different problem, and it's a different quantity, and so the axis here is position of the mirror rather than wavelength, and it's entirely different, okay? Okay, now with that, this tells us how to draw our arrows, yes? Because it tells us at what angle to draw the arrows. So I'm going to call these number 1, number 2, number 3, number 4, number 5, number 6, and so forth, and I'm going to draw the arrows corresponding to each one. So I don't know where it comes out, but number 1, say, comes out this way. And number 2 is a different time, quite a different time. Maybe less times. I at least should do that right. That's number 1. You might not like it because the arrows are small, but I better make them small, I get in trouble. Number 2 is at a different time. Number 3 is still less time. Less time means not turned as much. Number 4 is less time, and I haven't looked over here exactly how far I have to go. But after a while, less time, after a while the arrows begin to go more or less in the same direction. Why? Because when I'm down near the bottom here, all the times are nearly the same. Therefore, all those arrows, whatever their angle, they're all the same for a while. So if this was called 10, it isn't right, 11 actually, and this is 12. 13, 14, and so on, then this would be arrow 12, 11, 13, 14, almost the same. But after a while, I begin to climb up here. My angles begin to increase again. That is, they get parallel to the old ones. See, so they begin to turn over this way. And then as I begin to climb up this hill, as I change from dot to dot, the times change more and more each time, so that the arrows go more and more cockeyed relative to each other, more and more rapidly around that way. And they're just millions of them all going crazy. I mean, when you're climbing very fast up here, this arrow is this way, this arrow is this way, this arrow is this way, this one is this way. They're all different angles, so it's a big smear. And it was, in fact, if I went all the way back there, the smear at the beginning here. So I wonder if you can understand this, why I got that. I put together a lot of arrows whose angles, let's start at the bottom and go up this way and back that way. As we go up, we add the arrows almost the same angle, and then we begin to increase them faster and faster and make a little whirl. Back to the other way, it was symmetrical. I should have been adding arrows which are nearly the same direction, but all different angles and make a little swirl. That makes this kind of a curve, beautiful curve, if done very carefully, called Cornu's spiral. Swirl and more and swirl. Now, what's the answer to the probability of reflection? Geez, I forgot we were trying to find that. Oh yes, we start with the first arrow, which is somewhere down in the swirl down here, and find out where the last arrow is. Remember what the net result of all the steps. In other words, we're playing a game. You could almost do it in a room. You say to people, all right, make a step, turn this angle, turn this angle, turn less, turn less, turn less, now don't turn, now turn more the other way, and so forth, and they make this path. We want to know where they end up. And they would end up over here, which is a sizable arrow, and represents a good probability. So what? So we found that we do get counts. In other words, the mirror works. That's for sure. But what's all this business about the equal angles? Where did that come from? The only reason this arrow is long is because we have a succession of the pieces that are almost in the same direction. The parts in which the things are not the same direction don't make much difference. If we would cut the mirror off, throw it away, throw this part of the mirror away. I should have really, yes, it's better at the other end. It's the way it happened. Throw this part of the mirror away. Then that means that all the arrows from here on out are removed. They're not there because the mirror isn't there. Then this length is almost the same. In other words, we don't need that part of the mirror to get the reflection. Likewise, we don't need the part of the mirror on the other side where the things are changing fast. The only part of the mirror that we really need to get the reflection, we could throw the rest away, is just the section in which the times are not changing much. All right? Now, it's a geometrical thing that you have to figure out. Where is that? Where is the place when you move this around a little bit, it doesn't change the timing much? It turns out that's the place of equal angle. I'll show you why in a moment.
But if you decrease the size of the mirror sufficiently,
Yes.
then you get in trouble.
Yes. And then if you make the mirror too small, then it doesn't really work very well. Furthermore, it doesn't know about angles at all, because if you put this in any other position, you get that one little arrow, and it's the same size no matter where you put it. Any mirror loses its knowledge that it's supposed to be angles equal. You only get angle of incidence equal angle reflection with a mirror sufficiently large. That's rather small in practice. And so ordinary mirrors, you think everything's all right. Yes?
Seems to me you can test this theory.
Yes.
That this thing of adding up all these rows is correct.
Yes?
By very carefully taking all little segments.
You could. Why don't we cheat this? All right, good.
And get those things down.
I know it's 12 o'clock, but because you brought this up, and it's very interesting, let me continue a little bit longer.
Sure.
Okay. His suggests this. This sounds insane, what I just said. I mean, I'll put it my own way, but I'll come back. All this is canceling itself out. It's not doing anything. You don't need this part of the mirror. What I say from this crazy theory that I'm talking about is really kind of nutsy. I have a whole part of the mirror, which I compute a whole lot of little arrows, and it's happening, and the net result is nothing happens from that part of the mirror at all. It must be a myth that this stuff is happening. Why do I have to include all that junk? Right? Why do I have to add all those arrows which cancel out? They don't add up to anything anyway. I don't believe it. I don't believe that that really is reflected. But he says we're going to check it by a trick. The trick is the following. I think his idea is the following. Something like this. When you make the arrows, let's say down around in here, some of them pointing this way, and some of them are pointing this way, and some of them are pointing that way. For example, as we go along, from one point might be this way, the next point this way, the next point that way, the next point that way, and so on, right? Why? And then it comes around and goes around again this way, and it doesn't get anywhere. So he says, remove the mirror in just those places where the contributions would be going backwards. In other words, throw away the ones that are going backwards. Just add the ones that are going forward. As soon as an angle gets like they're getting ready to go backwards, erase the mirror, take them out.
Take out the middle too. Also. You just take out the middle.
No, just take those out, he says, where it's going the wrong angle. And then these are not there. So it doesn't come back. You remove. Then they begin to be the right direction again as they're coming around. Let those be back in. So we go this way for a while. As soon as it starts to go this way, remove them. How? By just erasing the mirror. What would happen if I carefully figured out which ones were giving arrows generally in this direction? In that general direction, if they have a component, so to speak, in that direction, the step is, although not precisely the direction I want, is less forward, I allow it. And when I calculate one that's pointing the wrong way, I simply erase the mirror, make a hole in the mirror in certain places, holes. Well, then there's a place you allow it, then there's a hole, then there's allowed, and there's holes. Well, the holes are made so that this will never back up. And then the result would be that we would get a very nice thing, and we would go blip, 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 blip. These are the sums of these arrows. And then it would go straight for a while, and then go blip, 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 blip. And we get a very strong and beautiful reflection. Even stronger than if the whole mirror's there. It would appear. And that works. You can do that, and it works. In fact, as he said, you can even do this so well that you can forget this part of the mirror. That's a good way to think of it. Let me take 2 more minutes and explain the same idea over again, but even more dramatically.
Take your time.
Yeah, let's suppose that somebody said, forget this mirror, it's not even there. What happens then? I have a mirror that's only so long, okay? I go back and I analyze, thanks, I forgot to do it that way. That's the nicest way to do it. I have a mirror only so long. Then in that mirror, all the arrows are just like this. They're adding, and then they go around fast. Everyone is different, because what I'm done is I'm only used this part of the curve. I never got to the place where they're all the same direction. So they're all different directions. You're going all over the place. So we get this thing going around, and it doesn't get very far from the beginning. The biggest it can get from the beginning is some short distance across here. There's not very much reflection from that. It all cancels out. Now we use his trick, that when the arrows are pointing the wrong way, in other words, as we make a contribution, we see it's this way, this way, this way, as we go along from one spot to the next. As soon as the mirror arrows start going the wrong way, like backwards, we erase the mirror. So what we end up with is a series of only the positive arrows, and are therefore able to get a reflection from a mirror which would ordinarily not reflect. If the whole mirror was there, it would not come any light, very little light would come there, because it cancels out. But if I erase the mirror in exactly the right places, let's take less mirror.
Less is more.
There, and to your sudden delight, there's a lot of light there. And that demonstrates that these parts really were having an amplitude to send light there. And the other parts were also had an amplitude to send light there, but it was opposite, and they were canceling. And this cancellation is not a myth, because by taking out half of it, you get a big effect. This device is called a grating. It's made the usual way of making it, instead of making it with the little pieces of mirror, although it could be made that way, just to make lines or slices on a plane. You may have seen these gratings. They used to use them in cars or something. Sometimes you see colored, white color on a sign, and as you turn, it changes colors and stuff. That's a grating. What happens accidentally is this. When I cut these things out, I have to figure out the time exactly to know which arrows go backwards. And that depends upon how much a difference in time means how much rotation. That depends on the color of the light. So if I cut this out so it works for red light, it won't work at this angle for blue light. It only works for the red light. It doesn't reflect blue light very well. However, it turns out accidentally that the mathematical places to make these cuts for red light, for this position of the source and this position of the detector, turns out to be correct, or nearly correct. For blue light, however, if the source was over there, the timings will change, but it still fits together. And the detector here, or vice versa, just changes the ends. When you turn it, it gives different color lights, so it's the same gradient. That's a little complication, but the main point is that this idea that there's a lot of effects in regions where you wouldn't expect them, like in parts of the mirror where angle of incidence is not equal to angle of refraction, is really right, because if I erase parts of the mirror there, I can get an enormous reflection from places where the angle of incidence is no longer at all equal to the angle of reflection. All right?
No matter how familiar one gets with that, there's always a bit of awe about that.
Yes, because the awe, it does not be awe if it were waves, you see. But when you realize that what you're doing is counting photons one at a time, and they decide to come or not come, you just figure this way. With this section of mirrors in here, they're coming. How in the hell, by putting more mirror in there, can I stop them from coming? But that's what happens. You get counts with the holes, try to fill up the hole, and you get no counts. Say, what's that doing? Well, and furthermore, if you have that little thing, suppose you had a little mirror section, the pieces that you took out, you put on another glass plate. So you could, so to speak, bring them up and take them away. But if you take them away first, you get a lot of light. Lots of photons are coming. Bring them up, it would be easier for the photons. There's more places to reflect, and nothing comes. Then take away the blacks, and leave just the greens, and you get lots of light. Both together, nothing. How does that magic work? The blacks making an arrow this way. The greens were all contributing this way. When I have them both, the net arrow is nothing. Either one is something. Either one alone, but both is nothing. That works fine with amplitudes. But to think logically about probabilities, it makes it very difficult, because you usually think if those would do it and the greens would do it, and you put them both there, they'll do it even better. So we can add amplitudes instead of adding probabilities. That is illegal. But adding probabilities is a long way to do it. You have to add the hours first and then make the square. Why? I don't know. Nature works that way.